Hello, good morning. We're just going to go through shear force and bending moment diagrams, a quick introduction, just to recap what we've gone over in class. Okay, so here we have a beam, two reaction forces, reaction force 1 and reaction force 2, and we've got a force here. Just to add to the confusion, generally in textbooks when you're looking at shear force and bending moment diagrams, in the equations and things, they'll use W for weight. Okay, so it's W for weight. So I'm going to use that convention just so we get used to that. As we know, weight is a force. It's the force of gravity acting on a mass. Yeah, as we've discussed, if you go to the moon, your weight changes because the force of gravity is less acting on your mass, but your mass is the same because the mass is how much of you there is. So this is where we start. So for a shear force diagram, it tells us where the maximum shear force is. If we remember, examples of shear force are a pair of scissors, for example. So anywhere where we get forces acting in opposite directions in fairly close proximity to each other. I don't suppose it matters really. Anyway, yes. So for a shear force diagram, it's fairly straightforward. What we do, we need an axis. So this is just like an axis of a graph. We need to draw our part to a certain horizontal scale. We need to make sure that it's accurate. So it needs to be to a certain horizontal scale. And then we bring down our construction lines. Obviously, you don't have to use construction lines. That's entirely up to yourself. I'm just doing them here for clarity. And then we start by walking along our beam. Okay. And when we get to our first force, so that's our R1 force here, well, I don't know. Shall we put some numbers on this and then we can unpick it a bit further? Go on, let's put some numbers on. Okay, so some numbers have magically appeared. Now, this is a very simple example. We've got our weight in the middle, so each reaction force will take an equal amount of that weight. So if our weight is 20 newtons, then that'll be 10 newtons either side. So we start to walk along our beam. We get to our beam, we hit the first force, and we go up 10 newtons. Okay, and then we carry on walking at 10, and we hit our next force, our weight, and we go down 20. And then we carry on walking along our beam and we hit our next force, reaction force 2, and we go back up 10. So let's put those lines in and see what that looks like. Okay, so here's some lines I made earlier. So we start off and we get to our first force and we go up by 10. So I'm doing a scale of 2 newtons to 1 square, so I've gone up by 5. And then we come along until we hit our next force. And then our next force is our weight, and that's down by 20. So we come down by 20, obviously that's 10 squares for my scale. And then we carry along. Okay, we carry along. And then we hit our final force, and that's 10 newtons up. And so we go 10 up. And that's it. That's kind of all there is to shear force diagrams. We walk along the beam. When we hit a force, we go up or down by that amount. So we'll do a slightly more complicated example of a shear force diagram. And then the only real wrinkle in the ointment for this is UDLs, which you'll remember are uniformly distributed loads. So we'll also have a look at how we tackle UDLs for a shear force diagram. Okay, so let's set up a slightly more complicated example for a shear force diagram and we'll just walk through that. Okay, so here's one we prepared earlier. We're going to assume we've already done the magic moments to find out our reaction forces here and here. And if you're struggling with magic moments, can I recommend stephenteacher.tiddlyspot.com, and right there under quick references, quick reference, 10 plus 1 steps to magic moments, and you just take some time to work your way through those steps and familiarise yourself, refresh your mind on magic moments again. Okay, any excuse to listen to a bit of Perry Como. Okay, so back at the math chat. What we need to do is we're looking at the shear force diagram for this. So again, here's one that I prepared earlier. So we start by walking along our beam, and we get to our first force, which is 18.75. Now this isn't going to be exactly to scale because I can't do 3/4 of a square in this program, so it's going to be roughly to scale. Okay, obviously you'll do better. So we go up by 18.75, and then we walk along our beam, and then we come down by 14. Okay, so let's get the right line. So that's going to take us to, should take us, let's try that again, to just before perhaps, we're not going to cross over. 14 maybe there. We're not going to cross over because 14 is less than 18, so we're not going to go back over. Okay, and then we carry on to walk along our beam, and we get to our 22 kilonewtons force. And at this point we go all the way down. Okay, so we're quite a way down there. Oops, daisy. We'll go down, and then we walk along again until we get to our final force. Just for clarity there, of 17.25, and then what we should find is that takes us back to the beginning. Now, obviously, if I was measuring that, properly, that would be more accurate. But it's not that. It's just a sort of quick example, just to show how it works. So all we're doing is we're going up by the force, we walk along to the next force, we go, let's get rid of that, we get down by the force, we go along, we go down by the force, we go along, and we go up by the force. And that's all there is to a shear force and shear force diagram. Okay, so next we'll just have a very quick look at what we do with the UDL, and that's, I think, everything we need to know for shear force diagrams, and that's exciting. Okay, back in a sec. Okay, so here we have a uniformly distributed load, and we can see that the uniformly distributed load is 5 newtons per meter. So that means that for every meter in length, we have an extra 5 newtons in weight. Okay, so how do we deal with it? The first thing we have to do, of course, is to calculate reaction forces 1 and reaction forces 2. So in order to do that, we need to deal with our UDL. And in order to calculate our reaction force 1 and our reaction force 2, we need to change our UDL into a point load. So how do we do that? Well, we take the total weight and we put that total weight at the middle of the UDL. So how much does this weigh? Well, first question is, how long is it? Well, it finishes at 9 meters over here, starts at 2 meters over here, so 9 minus 2 is 7. So it's 7 meters long, 5 newtons per meter, 5 times by 7 is 35 newtons. So let's just make a point load of 35 newtons. Okay, so there we have our 35 Newton point load, and we place that point, I've just grayed out the 5 newtons per meter there, and I've placed that point load in the middle of the UDL. So what that means is, it doesn't matter where our UDL is, our point load is in the middle of the UDL. So if our UDL is over to this side, and our point load is still in the middle of the UDL. So that's the total weight of the UDL, and we place that at the center of the UDL. So now we can do our magic moment calculations in order to find R1 and R2. So we'll do that very quickly. Okay, so the first step to identifying our moments, our reaction forces, is to pick a point we're taking moments about. So I've selected that little red dot there, R1. and we identify our clockwise and anti-clockwise moments. So if we're spinning around our little red dot, then our downwards force there would create a clockwise moment, and our upwards force there would create an anti-clockwise moment. So let's just put that into some maths. Okay, so just putting that in to some maths. Let's just move it a bit closer, why not? So we've got our 35 newtons there, force, times by 5.5. Now we know the definition of a moment is a force times distance, so if that 35 is our force, then our 5.5 must be our distance. Why is it 5.5? Where do we get 5.5 from? Well, our force is halfway along our UDL. Our UDL is 7 meters in length, so the halfway point must be 3.5 meters. So 2 plus 3.5 meters is 5.5 meters. Okay, and on the other side, our anti-clockwise moment is R2 multiplied by our distance 11. Okay, so we can now rearrange that and find R2. Okay, so 35 times by 5.5 is 192.5, and that still equals 11 multiplied by reaction force 2. So now to find reaction force 2, all we need to do is move that 11 there over the equal sign, so we get 192.5 divided by 11. Okay, so there we can see that 192.5 divided by 11 is 17.5. And of course, because we've got an answer, we need to put a unit there. What we found out, we found a force. So we've found R2. And now we can find R1. And for R1, we can say the up forces equal the down forces. So going down, we just have 35. Going up, we have R1 and R2. So R1 must be 35 subtract 17.5. So of course R1 is also 17.5 because our 35 newtons is in the middle. So R1 and R2 equal 17.5. Okay. Okay, so I've just put together a quick little sketch, I guess, just to kind of clarify what's going on and where the numbers come from. So here we can see we've got that 5.5, which relates to that 5.5 there, because that's the distance to our 35 newtons in the middle. All right. So just to help clarify things, yeah, we've got that extra step there. And we've got rid of our UDL completely, and we've just replaced it with the point load that's equivalent to that. All right. So we'll just move that out of the way for the moment. We might even shrink it slightly. Okay, that's a bit small, isn't it? Let's just put that up there for a moment, and we can leave that there. So what we now need to do is we need to draw the shear force diagram, which was the point of this. Now we've got our reaction forces, we can now do our shear force diagram and find out how we handle a UDL in a shear force diagram. So let's just set that up. Okay, so just like before, we start to walk along our beam and we find our first force and we go, right, it's not doing the snap thing. Okay, just imagine that these two things are in, oopsie daisy, that's not what we want. Just imagine that those two things are in line. So we go up 17.5, and then again we wander along the beam until we get to the start of our UDL, which is just here. And then we just stop for a second. We just draw a little line to the end of our UDL, which is here, isn't it? So now you know why I did the construction lines. At the end of our UDL. And then we come down by the total load of the UDL. So the total load of the UDL is that. So we come down by 35. And then we just draw a diagonal line from the start to the end point there. Okay, and then we carry on along our path, and then we find our final force and we come up. Okay, obviously I've got some snapping to grid issues there, so it's not quite lined up as it should be, but hopefully you get the general idea. Yes, obviously. This should be symmetrical as well, shouldn't it? So let's just make it proper. There we go. Yeah, that's what it should look like, because we've got the same distance either side, haven't we? We've got 2 meters there, and we've got 2 meters there according to the dimensions. This is why we should draw it accurately. And that's it. That's everything we need to know about shear force diagrams, really. You know, that's how we handle a UDL. We handle it just as we did in Magic Moments to find the reaction forces, and then when we're drawing our shear force diagram, we just put a diagonal line in, and that diagonal line is the length of the UDL and goes down the total load of the UDL, the total weight of the UDL. Yeah, so that's the length of the UDL there, and that's the total load down for the UDL. And that is, I think, everything we need to know about shear force diagrams. Okay, thank you very much.